Okay, so now finally we come to the pumping lemma itself. So what it is, and so in fact the lemma is very simple, and it's just proved in one slide, and it's very simple. So suppose this L is regular. Okay, so now we are taking a regular language. So that means there must exist some DFA which accepts this. Okay, there can exist some NFA or whatever, but we know that there's an equivalent DFA. So there must be some DFA which accepts this L. And suppose that DFA has n states. Okay, whatever that number of states is, it can be 5, it can be 50, it can be 5,000. I don't care, but there exists some n, right, for this L. And say these are the states, say from Q1 to Qn. And now if you take some string in this language, and the length of the string is at least n. So this n is a number of states here, and the length of the string is at least n. You see that length is m, which is at least n. So since this is in L, so there should be a accepting path. So this whatever this state is, this is a starting state, and it finally reaches a final state, and it passes through some intermediate states, and this is a DFA, okay, with total transition function. So there is no question of getting stuck or whatever. So there's a unique path for each z. So you take that unique path. So now the question is, how many states do you have on this path? You see, so you have m many edges for m many symbols, right? And you have m plus 1 many states here, right? But the number of distinct states, so the DFA has n many states, and this m is greater than or equal to n. So if you have m plus 1 many states here, so there must be some repetition, right? All these states cannot be unique. So each of these PIs is some Qj, right? So this Q1 to Qn is the set of states, and here I am just labeling the states in this paths with Pi. But this Q1 to Qn, they are all distinct states. So they are the distinct states of the DFA. But when I'm using this labels P1 up to Pm plus 1, so there should be some repetition here. So that means there should exist some I and j such that this Pi is Pj. Now, it's not just there is a repetition. If you consider the first n plus 1 states, okay, so you just consider the first n symbols. So from here to here, you just consider the first n symbols. Okay, so A1 up to AN. So if you are considering this thing, so then also you have how many states? N plus 1 states. So but there are actually n many distinct states, so here there must be a repetition. So that means there should be some I and j. Both I and j are within this part, so they are less than equal to n, such that this pi, they're less than n plus 1, because the last one is n plus 1 here. So yeah. So such that this pi is equal to pj. Now this is important. This I is not equal to j. You see, there are two different circles here which correspond to the same state. So this I is not equal to j. So this I is strictly less than j. So I is not j, but the states are actually same, right? So now this path actually looks like something like this, right? So you start from P1, you process this part up to I minus 1, so call this U, okay, A1 up to AI minus 1, so you process this part, and then you reach this PI, right? So then again you proceed to process this AI up to AJ minus 1, and after processing this you should reach PJ, but PJ is equal to PI, right? So what is happening in this V part is that you start from PI, and then you are processing something, and you are going about, and then you come back to this PJ after processing this V, okay, and then from here you process the rest of the symbols from AJ to AM, call that W, this together, and you reach this final state, okay. So I am not saying that there is no other repetition. Here also you may have some repetition, or you can have repetitions elsewhere also, okay, but that's not our concern. So all we are saying is that here in this V part, this V starts and ends with the same state. So no matter what happens in other part of the path, and this U part takes you from P1 to this thing, this common thing, and this W part takes you from this common thing to a final state, right? So we have such a structure if we have Z in the language, and if length of Z is at least n, okay. Now if we have this, you can easily see that if you take any UVIW, so then that will also correspond to a accepting path. So if you take just say UV0W, so which is just UV, right? Sorry, UW. So what will be that path? You come here and then you take this. So UV will be in the language because it gives you a accepting path. If you have say UV square, what will be this? So you come here, you take this V, and then again you take this loop and then take this W. So that is a accepting path. So now you can see, you can put any I, so accordingly you can make I many loops here, and then finally take this W to reach a final state. So you see that from this P1 with this string, this as input string, you reach a final state. So that means this should be in L. So this is actually our statement. So if L is regular, so we assume that L is regular. So if L is regular, then there exists some n, okay. So this n is actually the number of state in some DFA accepting that L, but in the statement of this lemma, that is not required. The only thing is that required is that there exists some L. Okay, so for any regular language L, there exists some L such that for all Z, if the Z belongs to L and if its length is at least n, okay, so this is saying that for all Z in L with length at least n, this thing. So if this happens, then there exists UVW such that this Z can be broken up into UVW, and this V is not empty. This V is not empty, you see, so that is why this I is not equal to J is important, right? So I is strictly less than J, so that means this V is not empty. And also this J is less than equal to n plus 1, that means this UV together, so you have processed some number of symbols, then you process some number of symbol, so this and this together takes J many symbols, right? Or what? Yeah, J minus 1 many symbols, and yeah, so up to this can be at most n, right? So after processing a J minus 1, you reach Pj, so UV together is A1 up to a J minus 1, and J is less than or equal to n plus 1, so this J can be at most n, right? So this and this together, it can be at most. So this is also satisfied. So it says that, yeah, again, for any regular language n, there exists an n such that for all Z in L with length at least n, this Z can be broken up into UVW such that this V is not empty. This UV is of length at most n. From here we have that, and for all I, this UVIW is in L, so that means this can be bound. Okay, so since we already defined pumping, so what does it say? That if a language is regular, then there exists some n such that all strings in that language of length at least n can be pumped. So this whole complicated thing here saying that this Z can be pumped. Z can be pumped. So you see that this definition of pumping required a given L and N. So it is saying that for any L there exists an N such that this part holds. This Z can be pumped. All Z of length at least n can be pumped. So then finally, if we write it down as a formal logical statement, so this whole pumping lemma is saying that if L is regular, then there exists a n such that any string in L of length at least n can be pumped, right? So L is regular implies there exists n such that this part, any string in L of length at least n, so this can be captured like this. So for all z in L and length of z greater than equal to n implies z can be pumped, and this was the thing. So if you see z can be pumped, so this was the statement for z can be pumped. So this I just plugged there. So that means there exists a breakup such that okay, so this is actually a breakup. This v is not empty. This uv is of length at most n, and for all I, this uviw is in L. Okay. So this is the formal statement for regular pumping lemma for regular languages. Okay, so this is what a pumping lemma is. So what will be the contrapositive form? So what was contrapositive form? So P implies Q. Its contrapositive form is that the negation of Q implies negation of P. So if Q is not true, then it implies that P cannot be true. So here we are saying that A is regular implies this part, that strings can be pumped. So in a contrapositive form, it will say that this pumping cannot happen implies that L is not regular. Okay. So this entire thing should be the negation of this entire thing. Okay. And what is this? There exists n for all z. Something implies there exists this thing, then conjunction of this big thing. So if you compare this with this expression, it's with this expression, it's exactly same. There exists n for all z. Something implies there exists this thing, and such that this, and for all I something happens. Okay. So this you compare with. So you can note it down in your exercise book. You just write it down on a paper. So there exists n for all z. Something implies that there exists UVW such that this proposition, and for all I, this proposition is true. So if you just compare it, this PQR, what are this PQR? So this is the P part. Okay. And sorry, this is the Q part, and then after this for all I, this is the R part. So this, okay. So this is one thing, up to this we have something, and then here we have another thing. So if we take a negation, what will happen? This will become for all, this will become there exists, and then this will become this conjunction negation of the rest of the part. So we have for all here, we have there exists here, so then we have this part, conjunction of this part, but negation of, conjunction of the negation of this part. So negation of this part is what? This then becomes for all. Okay. And this is the conjunction of this big thing and this thing. So the negation of this thing becomes this implies not of this. So this implies not of this, and not of this means this becomes there exists, and this is negated. Okay. again, you just try to see the meaning of this thing, not just churn the symbols. So this means that, so this is saying that for all regular language L there exists some n, okay, for such that for all strings of length at least n this pumping happens. So then this means that if the language is not regular, if it is the case that no matter what n you pick, you cannot make this happen, so then your language is not regular. So for all n, the later part should fail. Okay, so then that will mean that this L is not regular. So for all n, this part should fail means what? That means if you take some string with this constraint, so then this part must fail. Okay, so that's what it is. So for all n, if you take some string, there exists at least some string of length greater than n, such that this string cannot be pumped. And this cannot be pumped means for all breakup. Again, so cannot be pumped we discussed earlier, right? So cannot be pumped means for all breakup. So if the breakup satisfies these constraints, so this means that there is a breakup and these are the constraints, that this V part should be non-empty and this part can be of length at most n. So with this constraint you can find some I such that this pumped up string is not in L, right? That's what it means, that this Z cannot be pumped. So again, just pause this slide and try to see what's happening, and make sure that you understand it completely. Okay, just a half-baked understanding will not do. If you are not comfortable, you stop this and you go back to textbook and read through it, and whatever it requires you do that, but make sure that you absolutely understand the statement. Okay. So if this is the case, then L is not regular. So, and it's this contrapositive form that is that is the most useful to us, because we typically use this pumping lemma to show that some languages are not regular. Now let us go through some examples of non-regular languages, and we will show how to prove that they are indeed not regular using pumping lemma. So our first example is this one. So this language, okay. So 0 to the I, 1 to the I, so that means it has equal number of zeros and ones, and zeros first and then ones. Okay. So we will prove that this language is not regular. So what was our pumping lemma in contrapositive form? So we need to show that for all integer n, there exists some string in the language with length at least n, such that if you take all possible breakup of z, so it's a breakup of z, if you take all possible breakup of z with the constraints that this v is not empty and this uv has length at most n, so with this constraint breakup, all breakups with this constraints, we should be able to find some I such that this u v to the I w is not in L. Okay, so if we can show this thing for our language, then we can conclude that this L is not regular. So you remember that this z can depend on n, and this uvw can depend on sorry, not this uvw, this I can depend on all the previous variables, that is uvw, z and n, right? So Now we can write the proof in proof by contradiction form. So we say that if L is regular, then let N be the pumping lemma constant. Okay, so we generally use this terminology for this N when we are proving, because if this language is regular, then there should be some N for which the pumping lemma holds. So that N we can call pumping lemma constant. So this we can write as a, in a proof by contradiction form. So the first statement will be, let N be the pumping lemma constant, and N is a general variable, right? Because we are supposed to prove that for all N, so we cannot put any particular value to N. So the rest of the proof should go for any N. So so this statement is kind of written like this. So let N be the pumping lemma constant. So then we should show that there exists some Z such that the rest of the thing goes through. So that means we have to pick some particular Z, right? Not all Z. One cleverly chosen Z would is all we need. So we choose this Z to be 0 to the N and 1 to the N, and you see that this Z depends on N, obviously. So this Z depends on N, and also we must have this constraints, right? So Z must be a string in the language, and its length should be at least N. So both are satisfied because this 0 to the I, 1 to the I. So Z is in L, and obviously its length is 2N. Now you remember that finally we have to show that this Z cannot be pumped, right? So this part is that Z cannot be pumped, right? So this whole thing. And in a previous example we showed that the number of cases for all breakups. So since we need to consider all breakup, so the number of cases for all these breakups, they are sometimes very much simplified if we choose Z accordingly. Okay, so here we have 3 cases. So it's actually the same example. Okay, so here I have taken a particular value of N, but anyway, so there we are proving for general N. But anyway, here you see that this Z has length N, and here it has length 2N. So this is the thing that we are going for that proof, and here because the number of cases is greatly reduced, right? So so now once we choose our Z, and which should be guided by these 2 constraints, and also this thing that you must choose Z that this cannot be pumped, and this number of breakups, number of cases in the breakups, that is minimized. So this is sort of an additional thing to simplify the proof, but this is absolutely necessary, right? This Z cannot be pumped because we are trying to show that the language is not regular. So we have to choose Z in the language with length at least N, which cannot be pumped. So at least that property has to be there. So now we prove that Z cannot be pumped in this part. So here to here, so it shows that Z cannot be pumped, and for that, as I said, we have to consider all breakup, right? All this breakup with these constraints. So all breakup with these 2 constraints, and then what are the all possible breakups? Because UV together is of length at most N. So UV both are contained in this part, the 0 to the N. Okay. So both U consists of all zeros, V consists of all zeros. Okay, so U is some 0 to the k, V is some 0 to the L, and W is what is remaining. Okay, sorry, this is not KL, so this is so this there's a typo here, so this L should not be here. Okay, this L should not be here, so it's N minus K minus L. Okay. So, and this 1 to the N. Now this U can be empty, so this K can be 0 or something. Okay, but this L must be at least 1. Okay, so this L is can be 1 or up to N, but this L cannot be 0 because this is not an empty string, right? So this is the only possible case for our breakup, that U consists of entirely 0 and U can be also empty. V also consists of entirely 0 but it's not empty, and the rest is W. Okay, so now if this captures all the breakups with these constraints, so then we can choose our I, which can depend on all the previous choices, but here a particular choice is 0 suffices. So here in this example I mean we can just choose this to be 0, but in general I can depend on all the previous choice. So if we choose this, then this L many zeros are gone, because this is just L many zeros, right? So if we put 0 here, this part is gone. So if L many zeros are gone, then you have 0 to the N minus L and 1 to the L, and you see that it has less number of zeros than ones, right? So this is not part of this language where it has equal number of zeros and ones, so it is not part of the language, not a string in this language. So there we showed that this cannot be pumped. So hence, if you have proved up to this point, hence we can say that L is not regular, right? So this is the format for writing this thing. So here you have to cover all the cases. Here even incidentally it's just one type of case, one type of breakup, but here you may have many different possibilities and you have to cover all this, and these possibilities can be minimized by cleverly choosing this Z, right? So you choose Z which cannot be pumped and which helps in this part, and you choose your I here. So here you have to choose your I. Again, this I can depend on all the previous variables, and it should be such that this thing is not in L. So you have to choose I so that this is satisfied. And yeah, again, when you are considering all the breakups, so the breakups has to satisfy these two constraints, so that this part is non-empty and this part is of length at most n. So you consider all the breakups with these two constraints, and if you can do all these things and go up to this point, then you can conclude that this L is not regular. Okay, so let's see another example. So here the alphabet is just 0. Okay, so the alphabet is just 0, and what are the strings? So the strings, so the alphabet is this thing, and the strings are where the number of zeros is a perfect square. Okay, so 0 to the 0, that means epsilon is here, then 0 to the 1, that means 0 is here, then 0 to the 4 is here. So L is what? So L is 0 to the 0, 0 to the 1, 0 to the 4, 0 to the 9, and so on, right? So this is our L, and we will show that this language is not regular. So again, as I said, this step is kind of stated like this. So it's written as a proof by contradiction. So we say that if L is regular, let n be the pumping lemma constant. Again, we are not putting any particular value for n because we have to prove it for all n. Then you choose this Z. Again, Z, as I said, must satisfy these two constraints. That it should be a string in the language and its length is at least n. And just one such Z will do, and you choose the Z so that this Z cannot be pumped, so that you can do this part, that this cannot be pumped. Okay, and also when you are considering this breakup, the number of cases should be minimized. So that's how you choose your Z. And once you choose your Z, so here we are choosing this to be 0 to the n square. It depends on n, right? And then you have to consider all possible breakup with these two constraints. Okay, all possible breakup, but with these two constraints. So again, you see that everything is 0 because the alphabet is just 0. So Q is something, V is something, and W is the rest. But the point is, this UV together has at most n many zeros. So this K plus L, so this K zeros here and L zeros here. So this K plus L is at most n, right? And since this is not empty, this L is at least 1, right? Because V is not empty, so this is L is not 0, so this L is at least 1. So now if I choose my I to be 2, again I in general can depend on all the previous choices. So here this I equal to 2 suffices. So if I just instead of V, if I have V and V, so I have L many extra zeros, right? Because this UVW was the string, and now if I have one extra V here, V means L many zeros, so I have L many extra zeros, right? Now you see that this L is between this value because this is true and this is true. So by this 2, we have that L lies between this. It's strictly greater than 0, but at most n. So this n square L, you see that it's not a perfect square because you have n square, and what is the next perfect square? So it's n plus 1 whole square, right? So it's n square plus 2n plus 1. So from here, if you are going for a perfect square which is bigger than this, you have to add more than n, right? You have to add 2n plus 1 at least. But here you are adding something which is at most n. So this n square L is not a perfect square. So this, whatever this thing is, it does not belong to this language. Okay. So, and then we say that we have a contradiction. In fact, here we may add one more line that this Z cannot be pumped. Cannot be pumped. So we have a contradiction. contradiction. So it becomes a proof by contradiction, hence L is not regular. And similarly here again you can put that line here, that the same line, that Z cannot be pumped. So we have a contradiction. Hence L is not regular. So this is how you use pumping lemma to prove that certain languages are not regular. So later we will study closure properties, and we will see that closure property helps us to prove that certain languages are regular. Also closure properties helps us together with pumping lemma to prove that certain languages are not regular. But the basic tool for proving something is not regular is mostly pumping lemma. Okay, but pumping lemma is kind of one way, right? So if you can show this contrapositive form of pumping lemma, then you can prove that certain language is not regular. But if certain language is not regular, it's not guaranteed that you will be able to prove that using pumping lemma. But anyway, pumping lemma suffices for most of the cases. So that's it.